So CPE 133. This video is on multiplexers and their implementations using Verilog, commonly known as muxes. We'll also get into first concepts of generic modeling. So this is free-range Verilog Foundation Modeling Chapter 8. This is the first part of several videos. Disclaimer, I'm going to put this in all these videos, is that you're not going to learn Verilog by reading about it or watching videos about it. You actually got to go do it, write some code, and particularly debug that code. So I encourage you get started doing that. Multiplexers, it's one of our foundations modules. It's conceptually a very simple circuit. The implementations can get pretty complex, and that being the case, we are going to typically describe these with behavioral modeling. In fact, I've never seen one described with anything other than behavioral modeling. So this is a classic selection circuit in digital design, in that it will take one of these inputs and transfer one of these inputs to the output, and which one it chooses is based on this control input here. So this is a schematic diagram for an n-bit mux. We call it an n-bit mux because the data widths or the n value, and we just not specifying, it could be anything. Additionally, here it does have this distinctive symbol, so I don't know what it's called, parallelogram or wanky square, I don't know. Anytime we're going to use a mux in a circuit diagram, certainly we're going to use this distinctive symbol. So behavioral modeling, this is where we're going to implement our muxes with. It's a way of describing the behavior of a circuit rather than describing underlying logic. Typically what we use, consider high-level modeling, we're going to use procedural blocks to describe the circuit. There's two types of procedural blocks. There's always blocks and initial blocks. Always blocks are what we're interested in because those are the only things that are synthesizable. Later we'll be using initial blocks in verification, but not a big deal because we're not going to synthesize that circuit. So the always blocks contain assignment statements and particular procedural programming statements. Procedural programming statements are the if and case statements. We've worked with that a little bit before. We'll work with that more this time. Procedural programming statements, the procedural assignment statements come in two types, which is blocking and non-blocking. So it's kind of gets confusing, but it's easy rules to follow here. Essentially, we're going to only use the blocking assignment for combinatorial circuits, and what we'll see today is blocking assignments because with a mux it's a combinatorial circuit. So we talked a little bit about this before. It's becoming more apparent now, is that you're going to be assigning stuff to things, lack of better words there. So we've been working with wire types, wires, and reg. Okay, wires are a net type, regs are a variable type. So the wires we typically use in continuous assignment statements. We also use those to hook up modules after we instantiate them. So more on that later. The reg type is actually a variable type, and anytime we make any assignment from a behavioral model, which means an always block, the variable has to be declared as a reg type. So keep in mind that we have two assignment operators here, blocking and non-blocking, and they work essentially. The way we're going to use it is combinatorial circuits. We're going to use blocking assignments, sequential circuits, non-blocking. We haven't seen any sequential circuits yet. We'll get to that later. So our first example here is what we want to do is provide a model for this 4-to-1 mux. So it's 4-to-1 mux. It looks like the D inputs, the data input, it transfers one of those 4 inputs to the F output here. I forgot I can circle this. And which one it transfers is essentially selected by the select inputs. So there's four signals in this bundle. This select signal is going to pick one of those signals to appear on this output. So this is kind of clunky looking. What we want to do is translate it to a symbol that we're familiar with, which we've done here. This is essentially it's taking this D vector and pulling it apart for those inputs. So when for example, when the select value is 0, it selects this input to appear in the output. So typical multiplexer stuff. And so I'm just going to plop down the solution. This is one of the solutions, so we can look at it here. The input, the data inputs happens to be declared as a bundle. No big deal. We know how to get inside of this thing. Here's the other input, which is a select input. Single output, it's declared as a reg because, as you can see, we're going to be assigning that output from a procedural block, which is the always block. So moving on here's my always block. Here's the sensitivity list, and I've put every single value from the input, every single input into that sensitivity list. That's the way I'm going to do this unless I know better. Now you might say that I don't really need to do this. Maybe all I need to do is put the select input as a sensitivity list, and I believe that will synthesize properly, but I know for a fact that will not test properly. You won't be able to simulate that. Going through this list here, what I've done is use an if statement, and I have 4 if clauses there. Each one of them selects a different one of the D inputs to appear in the output. So you can see it here. I happen to mark these in decimal. Essentially, if you don't explicitly state what type of value that number is, it's going to assume decimal, which we've done here, and that's okay. So if the select inputs are 0, notice we use the equality operator, which is 2 equal signs. If the select input is 0, D0 gets transferred to the output, and etc., etc. A couple things to notice here: we got a single case, we've got a single if statement for every possible case. This is the right way to do it. Technically speaking, we wouldn't have to use this final else if. We could just rely on the else, but it gets kind of confusing, and I don't do it that way. Essentially, by the way this is written, it's a combinatorial circuit because it's an if, and it has a catch-all with the else. Okay, and in fact, the issue here is if it should get to that else statement, which it never will because I've completely specified the input here, it happens to assign f as a 0. So this is writing it this way with the else is a way of making it seem clear to humans reading it. Like I said, there's another way to do this, but I think this is the clearest way. So we can also use a case statement for this, and it's very much the similar idea. Everything's similar except the guts of this thing. So the issue here is the case selection is based on the select input right here. Essentially, here's my case statement. It has a case and an end case to delineate it. It has a begin and the end, which I actually don't need because there's only one statement here. The only one statement is, procedural programming statement, which is that case statement. So I could technically get away without the begin and the end. But for this example, I think it looks better with the begin and the end. I think it's more clear that way. So in the case statement here, I have my 4 cases here, very much like the other one. It's just a little bit different. Here are the actual selection variables. Once again, it's written in decimal, which is arbitrary. I could have put instead of 2, I could have put 2 tick B 1 0, 3 2 tick B 1 1, etc., etc. But that's the way I wanted to do it. It does have a catch-all statement, which is the default. It should never get to the default because we've completely specified. We've provided a case clause for each of the possible inputs, so it shouldn't actually get there. I do know that I think it's clear to do it this way, but I don't have to. If I specify every single input, I don't need a default case. I like putting the default case in there simply because it's modeling a multiplexer. A multiplexer is a combinatorial circuit, which means it needs to typically it needs to have a catch-all. So I like putting a catch-all in there. This is another example here. It's very similar to our previous examples, but we now are using buses on the inputs. So let's look at this solution here. Very much the same thing. Inputs before were declared as a bus. Now I've got them declared as 4 different 8-bit bundles. The output, of course, data with matches, declared as a reg because it's assigned from inside a procedural programming statement, which is the if-else, procedural block, which is always block. It's actually assigned by this procedural programming statement, which is the if statement. So it's very much the same thing. I'm checking for the select inputs using decimal, which is arbitrary. One thing I want to do here is notice that when I'm assigning buses here, you can see that the AW here is associated with the 0 input. So we'll put a circle around that. When I'm assigning buses like this, I don't have to assign the individual signals. I can make one assignment. It's going to do a bitwise assignment from the 8 bits of AW to F. And it does have a catch-all, even though I've specified every single case, which if I specify every single case, I can get away without a catch-all, but catch-alls look good. I do assign this 0 again like I did before, but this time I like to specify the exact width of this thing. If I don't specify a width, it defaults to 32 bits. And I think this is clear. It provides a little bit more information. So the alternate solution, very similar. I think the only difference here is that I've declared these values as binary rather than decimal as I did in the last solution. So this solution uses a case statement. These are all the circuit inputs as part of the sensitivity list, the always block. The always block does not have a begin and end because there's only one statement associated with that always block, which is that procedural programming statement, which is the case statement. One statement, I don't need a begin and end. Quite frankly, I think it looks better with a begin and end here, but whatever, just to show you that you can do it. Remember, the goal is to make your code clear and readable. So that concludes part A, and then we are on to part B.